a minimum that's about this wide and a dot that was my bright spot. So we just looked at the bright spot for diffraction grating. And here's the rule for diffraction grating. It should look really strange to you. Doesn't it look exactly the same as what we've been talking about? Yes. So it's not a new rule. So the idea of diffraction grating is we use the same information. The difference is, yes?
I actually don't want to, I mean, so with the visible spectra, right? Why is it that lowest intensity, like the lowest intensity is bluish, right? Purple? Or sorry.
Are you saying what intensity or
I'm comparing like the artistic spectrum to like scientific spectrum. Like why do we see red or purple as being a combination of blue and red, but the wavelengths are so different? Does that make sense?
Oh, no, it doesn't make sense at all because it's the same. No, what I mean is it's a great question with absolutely no answer.
Oh.
Because God made it that way.
Okay.
And what we see with our eye has nothing to do with physics. It's pure physiology. In fact, I just had, not an argument, but a discussion with two of the other professors in the department this morning where I showed them they were wrong and I was right. Which is it's the first time in my life, so I'm hanging on to it. No, actually, they didn't disagree with me. They just never thought about it before. When you have soap bubbles and you get a film of soap bubbles and you let them hang, on the thinnest part, you'll always see a yellow band. And most textbooks will say that that means you're getting enhanced yellow light, and they calculate the answer based on that. That's absolutely impossible. It turns out it's happening because you're canceling blue light, and our eyes, not physics, if you were to use physics, you wouldn't get yellow. Our eyes see it as yellow when blue is missing. And the reason for that is because blue is the shortest wavelength, so that's the first one that will cancel. All right, so the reason, or answer to that, I really don't know. I don't think, you can't know it, it's just how the eye is made. All right, so basically coming back to this though, is they give me a diffraction grating, and when you get diffraction gratings, even though this is the equation, D is never given. What they'll say is we have 10,000 lines per millimeter. And I could go through a lot of rigmarole to prove this, but it's not entirely true, but it's 99.999% true, so we do it because it's easy. When something's 99.999% correct, and it's easy, as compared to the really hard way, we do the easy way. And that is that D is equal to 1 over 10,000. Because if this is lines per millimeter, by flipping it I get millimeters per line, which is the separation between adjacent slits. There. All right? But I'm off a little bit because if I have 3 lines, the separation is only between 2 of them. So you should be down a little bit. If you do 9,999, it's not going to be enough different to even care about. So we just use the full thing here. Y'all got it? You're going to have homework on this. So they can give you, this is how many lines it's got, and you calculate D from this. Once you calculate D, then we come back to our famous whole equation. We know what to put in for D. If they tell me I'm looking for the first one, I put M as 1. All right? So it turns out that if we could, in a dark room, we'll see this in the lab. But what happens is that when you get your first rainbow, which is we call the first order, dead center is white. You look to the second, and you get a full rainbow. That's called M as 1, first order. Then the next one gets spread out bigger, and that's the second order. But it spreads out so much that the third order overlaps it. So there's no clean gap between second and third order already. Because if you have this many lines, it spreads it out so far. So that being said, they say we have 900 slits per centimeter. What's D? 1 over 900 centimeters, right? Good. All right, and they tell me L is 2.36. What's L? How far it is on the diffraction grating to whatever screen we're looking at, right? And then they asked me to find out that I've got 2 maxima from 2 different wavelengths are 3.06 millimeters apart in the first order. Okay. Stop. In the first order tells me what? M is 1. Done. That's easy. Then I say, okay, the 2 occur 3.06 millimeters apart. I don't know exactly what the values are, but I know that that's how far apart they are. So what I did is I blindly said, let's get started and pretend I know what I'm doing. And I know that D, y1 over L, which is d sine theta, equals lambda 1. Why?
Sine theta equals tan theta.
Because it should be m lambda, but m is 1 because they said first order. All right, and then I know dy2 over L is equal to lambda 2. Right? Then, and actually I wish I had that question in front of me, because apparently I didn't quite write down as much information as I wanted to have. 2 maximum. Does somebody have their homework in front of them? What, there's some information I didn't write down here.
Yes.
What information did they give us?
For the same problem I have.
Yeah.
Let's see. Visible light passes through a diffraction gradient. And it has 900 slits per centimeter, so same thing. And then interference pattern is observed on a screen that is 2.34 meters from the grating.
Okay.
In the first order spectrum, maxima for 2 different wavelengths are separated on the screen by 2.94.
Okay, which is different from mine, but not a problem.
And what is the difference between these wavelengths?
Ah, all right. So if they asked me to solve for the wavelengths, that's where I can. So I didn't write what the actual question was. All right. So we're good. They just want to find delta lambda. So guys, we've got everything we want because look, delta lambda by definition is L2 minus lambda 2 minus lambda 1, right? That's what we're looking for. But that, by what I have over there, is just dy2 over L minus dy1 over L, which equals d over L y2 minus y1. Right? This was given to me. The difference between the y locations is given in the problem, and d and L are also given. Because d is 1 over 900, and L is how far away the screen is from the interference pattern. So that solves for my delta lambda. Yes?
Yes.
Okay. Yeah.
So for y1 calculation, you always consider the first axis at 0 point, right?
Yes.
I mean,
I'm not sure. Maybe I didn't
I
understand.
mean, when the light comes out from the source.
Yeah, the dot in the middle is always the 0.
0.
Right. Okay, so then they gave me another one. They said I've got a lambda of 656 nanometers. Is that visible?
Yes.
What is it? 656 nanometers? Yes, visible. Any idea what color?
Towards red.
You erased it. I heard somebody say.
Towards red.
It's red, right? Because we had 630 was red, and it's even longer than that, which means it's just redder. All right? So it's red. And then we also have lambda 2 is 410. Any takers? What's the lowest wavelength? Yeah, it's purple because 400 is purple, so that's not very far. So we're still at purple. So we got purple and red, the two ends. All right, and we get these lines from helium gas, hydrogen gas, on a grading of 5,300 lines per centimeter. So you know what to do with that, right? I know how to get my D. All right. Then they say the first order. Find where they land for each of the angles where each color lands. So I come here, and well, actually, that's too special. I come here, d sine theta equals m lambda. They gave me the two wavelengths. They said in the first order, so I know m, right? And d, they gave me 5,300, so I can easily find the spacing. All right, and then at that point, it's very easy to solve for theta. That's all it is. So just go ahead and solve for theta for each of the two colors, and that'll tell you what the angles are between them. Do not make the assumption for this that the angles are small enough to use y over L, which we don't have anyway, but actually take arctangents because it turns out, as you saw with the diffraction gradients, that you get a lot bigger angles than what we're used to. So actually, go ahead and solve it that way. And the very last one I wanted to get through, so I'm going to have to talk fast because I've got 3 minutes. Anyway, this is number 17. Basically, they say I've got a wavelength of 630 nanometers, and the first order Y for the 630 nanometers is at 0.29 meters on the Y, and they give me a Y value. They also asked me to find out if the second order is some other number, all right, and they say what angle is that going to be, but they don't give me L. And they say, well, go ahead and find out what angle that is. All right, so what did they give me? They told me that I've got, I know how high on the screen it's going, all right? So I know that I've got the first order one, they tell me it's 0.29. They tell me that the first order, the other color is 0.19, so they give me the heights on the screen of both of them, but they only give me the wavelength of one of them, and they want me to find out what wavelength the other color is. How do I go? All right, so it's not going to surprise anybody, is it? This is where I start. Right, because it's telling me, this is the whole thing, is we're doing d sine theta equals n lambda, and that's what we've been doing all day long, literally. All right, so yeah, this is where we start. And they said, I've got y1, I've got y2, and this is associated with 630 nanometers. All right, and so what's happening is I'm starting at some distance L, but I don't know what that distance is. And so I draw these two lines, okay, and I say, what wavelength made this one? Well, let's solve this for wavelength. M is 1, right? So I have lambda is equal to d sine theta. Duh, all right? Sine theta is equal to y over L. So lambda 1 equals d y1 over L, and lambda 2 is equal to d y2 over L.
Where do we know to use these, the y1 over L? Because some use it that
But no, what I'm saying, what I said don't is because we don't have the information to do it.
Okay.
So when y is given, that's when you use it. When y is not given, you stay. All right. Also, on the diffraction gradient, typically you don't do it because the angles are too big to make the approximation. But that's not what's going on here. All right. So guys, do you see what to do from here? Make ratios. Ratio. D and L cancel. I know the two y's. I know one of the lambdas. I can find the other one by simply doing ratios. That's the other big physics trick. Do ratios when you've got the same unknowns in both equations. That cancels the unknowns. All right, I have 10 seconds to say get out of here, and bring your little things up and stick them in the little wooden tub here. Is that a question, John?
Yeah. So we're assuming that M is going to be the same.
This is the first order.
Okay, so
At least I go first order on my notes. I don't have the questions in front of me, but I didn't get very much.
It'll tell you second order.
You can't do this. I don't know when finished through. Yeah, they do. They tell you first order.
With this problem here you were showing us, gives you